Excellent. I want to welcome you to EurekaFest and the presentations in this group one from 3 of our high school invent teams and 2 of our collegiate student prize winners. This is an opportunity for you to hear directly from these inventors that we're celebrating at EurekaFest. I hope you were able to see the kickoff with Dr. Seema and our additional guest on energy as an outstanding presentation. My name is Don Domes, and I led InvenTeams as a high school teacher about over 10 years ago, and now I'm a master teacher and I provide assistance to high school teams and their teachers. I'll be your MC for today. There's going to be a time after each one of the presentations for you to ask questions. Please post your questions in the chat area or in the Q&A. And let's get this started. Our first presenters are the InvenTeams students from Energy Institute High School in Houston, Texas.
Hello, can everyone see the screen? All right, awesome. My name is Ben Barnes. Welcome to our presentation by the Energy Institute High School Invent Team regarding our proposal to repurpose current 3D printing technologies in order to more effectively and efficiently recycle waste PLA filament.
And here's our invent team from the top left corner to the bottom right. First, we have Ben Barnes, Oscar Davenport, Dia Patel, Kendall Towser, Risa Deshev, Ian McDaniel, Bella Johnston, Ali Kirshen, Orion Caldwell, and Noah Height. And we're located in Houston, Texas.
Although 3D printing has created a plethora of opportunities that are accessible to many, it can also pose as a form of pollution. 19% of all 3D printer filament is wasted, which adds on to the pre-existing plastic waste. In 2019 alone, 9 million tons of plastic waste, which is roughly 4,000 space shuttles worth, were added to the world's oceans and rivers. This is a detriment to our environment, and it is crucial that we find a solution to make technology sustainable.
Because our product is all about 3D printers, there's some important information for us to understand regarding their parts and functions. Starting on our left, we have a spool of filament. This is pretty straightforward. It is a spool that holds the 3D printing filament. This filament is then fed through a Teflon tube that guides the filament all the way to the extruder. The extruder melts down the filament and then extrudes it onto a build plate that we see in the picture. Lastly, we have stepper motors, which are just little motors that help move the extruder along different axes. All of these parts allow 3D printers to create elaborate prints that then let us to our problem and solution.
Throughout high school, we worked on different projects that often involved using 3D printing technologies. And one thing we noticed is that after our projects, we had a lot of PLA waste filament in the form of skirts, brims, or support materials, as well as failed prints. And this just contributed to the bigger issue of 3D printing waste, which is why we decided to try and create an affordable solution to recycle PLA filament.
So some of the initial things that we looked at while looking for prior solutions were that we saw that there was something called the Philibot EX2 extruder setup and the shredded shredder. So the Philibot EX2 is an extruder that essentially takes a shredded plastic and it puts it into a spool of plastic that can then be used by a 3D printer. And the shredded shredder basically takes wasted PLA filament and then can shred it down into that grain that could then be used in something like the EX2. However, both of these solutions are extremely expensive. As you can see, the Philibot EX2 is around $6,000. So it's not very accessible to a hobbyist or someone just looking for a cheap, easy way to recycle. Even for large companies, it's a really large investment considering what it is. So we think that we can try to reduce this price.
Another prior solution or another couple prior solutions that we looked at, one of which was the Protocycler, right? So it's very similar in design to the Philobot. So it pretty much grinds up waste 3D printer plastic, melts it down, and then re-extrudes it into a spool of filament that you can kind of see on the left. And although it is slightly cheaper than the Philobot, it is still like, it has a very hefty price tag of $3,500. So it's still not that accessible to like hobbyists or just general 3D printer enthusiasts. And then there are two other pieces of technology. So there's shredders and pellet extruders. So a shredder is essentially just a kind of machine that breaks down, I guess, like items into small little particles. And this can be applied to waste plastic, right? Because we can put plastic into a shredder and it can kind of break it down into little plastic pellets. And then these little plastic pellets can then be used in a pellet extruder, right? So they can be melted down and then re-extruded onto a 3D printer bed to make like a finalized print. And we have, in our like prior solution research, we have not found a kind of system that combines both shredders and pellet extruders kind of into one whole system of 3D printer waste recycling.
Yeah, so to that end of recycling wasted PLA filament, we designed the filibuster, as you can see here. This is our final solution schematic. So on the top, just situated over that 3D printer crossbar would be a filament shredder into which waste PLA filament would be inputted. And then the effluent would travel down some sort of tubing. We thought Teflon tubing would be a good plan for that particular component. And then it would arrive at a pellet extruder, similar to the one that you can see down here. That would be custom made to be compatible with the Ender 3 Pro 3D printers that we use at our school. And then that pellet extruder would output an end-use part. And the idea with this was that it would be a direct way to re-extrude and recycle waste PLA filament. Because as Noah said in a couple slides ago, technologies that currently exist typically take that waste PLA filament and then make it into a spool, as opposed to taking it and converting it directly into an end-use part. So this was the plan that we decided to pursue.
The shredder is one of the most important parts of the entire product along with the extruder. It's what allows the waste filament to actually be converted into these small little scraps that can then go through the extruder and be turned into an actual object again. And it only takes PLA filament is what was used for now. And in the bottom right, you can see a wooden prototype of the pellet or the shredder, as well as the side plates, which would then have the gears and shredder itself mounted to it, along with panels that would funnel the waste plastic in. In current plans for the shredder, the site profile revision is complete. It's what you see on the screen. And so before, there are these panels that go onto these plates. It's where the squares are on the CAD that you see there. That would then guide the plastic to go down the correct path instead of skirting around all of the individual grinders. However, there have been issues with assembly, most notably that lots of people haven't been in person this year, and real parts have not currently arrived, so a blender is being used to test the pellet extruder.
For our goal to reduce plastic waste, we have constructed a mechanism that will help in this process. This device is called the Pallet Extruder. What is a pellet extruder? A pellet extruder is basically a part that combines a pellet melter and a pushing mechanism such as a screw and a motor in one device. This mechanism will replace extruder on a printer that uses a spool of filament compared to our design that instead uses scraps of shredded filament in our filibuster device to recycle PLA. The parts for a pellet extruder consist of the motor, coupler, basin, barrel, hot end, and the nozzle. So how exactly does it work? Well, the first steps are shredded pieces ground down to the appropriate size will be loaded into the basin next to a screw, motor, and the barrel. The motor rotates the screw that will act as an auger to push the filament down the barrel to then be heated by a heat block. The plastic will then melt and is actively pushed down the barrel in its viscous molten state to through and out the nozzle to print any 3D part. Here are some pictures of our CAD and constructed prototype. Here's our core design in our pellet extruder. This part is what connects each piece together and mounts it to the Ender 3 3D printer. The importance of this part is that it's a cheaper alternative compared to currently marketed pellet extruder kits. This part takes advantage of systems already part of the 3D printer with the purchase of a barrel and screw to easily convert your home printer into a pellet extruder. Here's some pictures.
So as Ian said a couple of slides ago, we were never able to actually arrive at a completed and physical version of our shredder. However, that didn't stop us from testing our pellet extruder on the Ender 3 Pro 3D printer. So what we did, as you can see from these images, we affixed our pellet extruder to the ordinary extruder position on the Ender 3. We raised that limit switch on this left-hand side here so the nozzle wouldn't crash into the bed. And then we ran a print. So we had to adjust some of the slicer settings before we ran this print because the stock stepper motor that came with the Ender 3 Pro printer that we used, the feed speed was initially too slow. So we jacked it up to like 3,000% or something like that so it'd be compatible with a pellet extruder. And then what we did as it was running, this is the image you can see here on this left side, was we observed whether or not the shredded pieces of PLA would actually be forced down the auger and out of the nozzle. And what we found upon our tests was that the stock stepper motors that came with the Ender 3 printer were not actually strong enough to push those pellets all the way down through the barrel. So that was like the lingering extrusion issues that we talked about in this bullet point right over here. But we have since updated both the screw and the stepper motor to be like of higher torque and to just have more space around the central axis of the screw. And we're planning on running tests as soon as all of those parts get revised so that we can hopefully have a successful print with our pellet extruder. And just as like a price comparison, this product right here cost around $85, and pellet extruders that are currently on the market that we found cost like upwards of $400. And this could be easily printed and installed by your average 3D printer enthusiast. So we think it's a massive step in the right direction in terms of pellet extruder technologies. So some of our next steps, again, for our shredder, the name of the game there is just to, once all of those parts arrive, convert our CAD model into a physical product that we can actually test, on the 3D printer crossbar. And then for the extruder, as you can see in this bottom picture, we have updated that stepper motor and that coupling system so that it can more efficiently and more effectively push those PLA pellets all the way through that barrel. Yeah, and then after that, we'll just retest the extrusion capabilities with all those additional parts. Now, three of the things that we learned during this project in these unprecedented times, right, were the importance of deadlines, especially in virtual groups. So we wanted to be cognizant, as team leaders, of all of the commitments that our other team members had throughout the course of this project. So we were kind of lenient with the deadlines that we had. But I think going forward, it would really behoove teams like ours, and maybe teams in the future, if we ever participate in similar teams, to have more rigorous deadlines so that we can make consistent progress and not stagnate ever. A second thing is communication. We just used the Microsoft Teams platform for communication, but that wasn't ideal because not everyone checked Microsoft Teams outside of school, which is like generally when we use Microsoft Teams ordinarily. So we think that a better communication system would certainly have made progress more consistent. And then the final thing, of course, in-person meetings. We met virtually for over half of this project. So yeah, I think if we'd really attempted to get those in-person meetings, start actually constructing those physical prototypes, we could have made a lot of significant progress, which we ended up doing when we, towards the end, created our pellet extruder in its physical form. So yeah, those are the three things that we have learned and are trying to improve going forward.
Thank you so much for taking the time to watch our presentation. We want to give a special thanks to Rod Champagne, Jessica Marino, Jordan Campbell, Lauren Christick, and Lauren Baird, who all of really helped guide us, especially a big thanks to Miss Christick and Miss Baird, who were our teachers for this entire time and really helped mentor us and made sure that we did everything that we needed to do. We couldn't have done anything without them. We also want to thank everyone at Lemelson MIT who helped us along the way, especially Alma, who did all of our purchasing when we unfortunately lost our a debit card through MIT. So really thank you to her, and thank you to Tony for helping guide us. And finally, thank you to the juniors on our Invent team who really helped pick up the slack when the seniors had to deal with everything that involves with college applications and things like that. So thank you so much, everyone. Thank you so much.
Thank you. That was a great presentation. We've got a few questions. First, how do you de-air the recycled material after it's gone through the shredder?
Oh, that's a really good question. So we actually haven't looked into that at all. The idea behind the shredder being situated, if I could go back a couple slides, the idea behind the shredder being situated, far above the actual pellet extruder would be that as the pellets kind of traveled down this tube, they would start clumping up, and so the air pockets that could be, theoretically present towards the top of this tubing would be largely eliminated. But yeah, that's a really good point. I guess we'll have to look into if we make any further, updates to our pellet extruder. So thank you.
Good. We've got another question. What type of material is the shredder core made of?
So I believe, correct me if I'm wrong, the guy who designed the shredder was unfortunately unable to be here today, but I think we decided on steel, using steel. We were originally going to use aluminum, I believe, but we were recommended by Rod Champagne, who's one of the people in our acknowledgement slide, to use steel as an alternative.
Yeah, I think we're going to use steel for like the base kind of like structural part of the shredder, right? And then we're gonna 3D print like a lid and a shroud just to make it like safe for users, so no one loses a hand while trying to recycle waste plastic.
Well, all of us that have used 3D printers have dealt with clogs and nozzle plugs and material not moving. How does the pellet extruder experience those clogging issues when shredded pieces start to flow to the extruder? And how do you overcome that so that you get a nice even flow out of the extruder?
Or you want to take this one?
Yes. So during our testing, we were trying to test the shredded pieces going down the barrel. And so we were having some heating issues trying to melt the plastic. And so we haven't had enough testing, but we were going to change our heating mechanism so that we could melt the shredded pieces in the barrel rather than at the nozzle, because the plastic wasn't being melted. But we were having issues with the screw pushing down. It was actually clogging. So with the motor that we had, but we have a new motor. We haven't tested that one yet. But we were having issues initially with the force needed to push the shredded pieces down. But we think that once we change our heating mechanism and so that we can heat the barrel, that we have fewer issues with that.
Excellent. Thank you. This is a very exciting project. Great job, you kids and instructors on this project. So our next presentation is a Collegiate Student Prize winner, Paige Balcom, and she has information for us on her invention, and it's in the Use It category. Paige?
Thanks, everyone. Really happy to be here. I love being able to come after that great presentation because I'm also working with plastic waste. My name is Paige Balcom. I'm a PhD candidate in mechanical engineering, majoring in heat transfer and minoring in development engineering. I'm a co-founder and CTO of Taka Taka Plastics, which is what I'd like to share about today. So we all know that plastic waste is a really big problem across the world. Only 9% of the world's plastic is recycled. And this problem is even more severe in developing countries, where 93% of the waste is burned or dumped. And we know that, of course, burning plastic is really terrible for your health and for the environment. It releases all kinds of toxins and carcinogens and greenhouse gases that are not even accounted for in global inventories. And then comparatively, in high-income countries, only 2% of waste is disposed of improperly in this way. Africa in particular has the worst solid waste management of any region in the world. And Uganda, specifically where I work, produces 600 tons of plastic waste every day, which is the equivalent weight of 331 cars. So I was able to spend, I've been working on this plastic waste problem for the last 4 years and have been able to spend a lot of time in Uganda, actually on the ground, interviewing people and getting to know what the problems and solutions have been. And so from my fieldwork, I identified 2 major problems in Uganda's big plastic waste problem. And the biggest one is PET plastic, or polyethylene terephthalate. And that's the kind of plastic that water bottles and soda bottles are made from. So we're all really familiar with this type of plastic. It's one of the most common forms of plastic waste in Uganda, but there's currently no way to recycle it in all of East Africa. It used to be that the few bottles that could be collected were shredded by recyclers in the capital and then exported to China and India. But in the last few years, since those countries have stopped importing plastic waste, that's no longer an option. So the bottles have just been piling up and overflowing out of the gates of these Kampala recyclers. The other really big problem that I identified is, I call it waste sinks. It's a term that I coined to describe areas that have a lot of plastic waste, but they don't have access to recycling. So for instance, Gulu, the town where I work, it's 6 hours drive from the capital where those recyclers are located. So transporting low value plastic waste 6 hours just is not economical. So the plastic is stuck in Gulu. And like Gulu, there's thousands of other waste sinks across the developing world. So I knew that to develop a solution, we needed a local distributed solution. Like instead of having large centralized recycling plants, we needed to close a loop in a local circular economy. So I partnered with a Ugandan colleague. His name is Peter Apoko. He's a lecturer at the university and was a community activist. And together we founded Taka Taka Plastics. And Taka Taka means waste in Swahili. So in our model, we collect, process, and like melt the plastic, and then mold it into new products that we can sell all in the same community. So we're creating that circular economy in that local context. And we also were able to figure out how to solve the PET challenge. We're the only company that can actually recycle locally the PET plastic in Uganda. So we developed a proprietary process and machine to be able to alter the chemical structure of the PET just enough to be able to make a strong product. Because usually when you melt PET, the chemical properties make it really brittle, so it just cracks and crumbles. But we change the chemical properties a little bit and make this, these wall tiles for kitchens and bathrooms. And they're really strong, stronger than the ceramic tiles that people use now. And you can customize the design, make different colors, different shapes. So people really love them. We actually are trying to increase production because we can't keep up with the demand. And then during COVID, we actually pivoted our production process to make face shields to be able to help provide this PPE to hospitals and schools and police officers because Uganda faced a dire lack of PPE. But the thing that I love about Taka Taka Plastics is that we're able to use technology and engineering to really change people's lives. Like we're taking waste, something that people see as just rubbish and it has no value. And we're able to use engineering and technology to actually transform that into something valuable. And then through that process, be able to create opportunities that are changing people's lives. So like our production team is comprised of former street youth. So it's the street youth are able to actually have a job and be able to have, we give them free meals and just have that community of support that they get to come to work every day and earn their own living and be able to have food for themselves and rent a room and even be able to connect back with family and support their friends. Some of them are going back to school, even starting their own little small side hustle businesses. Give them access to savings groups, and all of our staff go through trauma counseling. So I just love how we're able to use engineering and technology to really have that community impact. So Wearable Tech, thank you very much. I'd be happy to answer any questions and just tell you more about our awesome team.
Thank you very much. Can you tell us any idea how many tons a year they're able to process?
Yeah, so that's a good question. Right now, we're still scaling up, so we're only processing about 1 ton of plastic every month, but our goal is to get to 9 tons of PET every month, which is about half of the PET waste in Gulu. But eventually we hope to even expand beyond Gulu and go to other towns across Uganda.
Excellent. What can you tell us about the process of converting the PTE into the tiles? That just looks really interesting.
Yeah, so it is a multi-step process. Let's see, I can share. So this is the core part of the technology. This is the injection machine. This is where we melt the plastic. So, but before getting to that, first we have to collect the bottles. And so we have a network where we work with different hotels and restaurants, and they give us their bottles, and people also just bring it to our office. So we first collect the bottles, and then we have to shred it into small pieces, and then we wash it. And then we take those flakes, the shredded PET flakes, and load them into this injection machine. So this is a machine that we built and designed locally in Uganda, and it's about 1/3 of the cost of if you were to import a similar machine. But it can be easily maintained and in Uganda. And so we specifically designed this to be manually operated. So you load the plastic up here into the hopper, and then this is where the heaters are. So you melt it, and then you would put the mold underneath. And this is the giant wheel is where someone would turn and be able to apply the pressure to inject the plastic into the mold. And you can make all different kinds of products just by changing the mold. And so the unique things about this is, we're able to precisely control the temperature at which we're melting the plastic, because that's really important. Each different type of plastic has a different melting temperature range. And if you go beyond that range, that's when you get the toxic fumes that are bad for your health and bad for the environment. So depending on what type of plastic you're melting, like PET has a melting temperature of about 265 degrees Celsius. And so you want to set it to maintain that temperature. And then, as I mentioned, we specifically designed the machine to be manually operated so that instead of paying for electricity and maintaining expensive equipment, instead we're creating jobs. So we pay the former street youth to come and be the production team that actually runs the machines and makes the products.
Well, someone wants to know, are these tiles available here in the United States, and what do they cost, and where would you get them?
We're working on that. So far, they're just in Uganda. We sell them for about 22,000 shillings per square meter, which is the same price as the ceramic tiles on the market. But yes, we're working on getting to the US market as well.
Now, do you have to sterilize or clean the raw material?
So we do wash the plastic, and that removes the large chunks of dirt. Since it's just in a construction application and not food quality, we don't sterilize the plastic. But yeah, so for the construction purposes, but also the melting process also helps clean it and remove any contaminants as well.
Can you share with us a little bit about your experience of going to Uganda and asking the local people what they need? This is really exciting.
Yeah, that is a really important piece of the design and engineering process that in engineering school, we're not taught that much about listening to the local community, but it really is the most important part, because you can have these great technical designs, like the equations can all work, but if you're not actually solving someone's problem, if you're not actually meeting their needs, then it's all for nothing. So it's really, really key to work with a local partner who really understands the local community and understands people's needs. Because as as an American student, like I can go into Uganda and I can I can go to hardware shops, I can go to contractors and builders and I can like show them different products of plastic construction materials that we could make and ask them like, oh, would you want this? Would you want this? How much would you be willing to pay for it? And yeah, they can get really excited and they'll tell me that they would love to use plastic tiles or plastic lumber. But if you can go with a local colleague who can really be able to interpret maybe the things that are not said exactly and really be able to give you an honest evaluation of what the local community is really looking for. Yeah, it really helps create a project that is really filling the needs of the community and will be able to be sustainable long-term. Like you don't want to just show up for 2 weeks and do the project and then leave, because that's not being able to really listen to the needs of the community and also not be able to maintain long-term. You really have to make that commitment to be able to spend significant time understanding the context, even beyond your problem, and really listening to the people that you should be like actually designing it with them, not just giving them a solution.
This is so well expressed. Listening to the customer, getting to know the customer. That is absolutely key if you expect them to actually use it when you've got done inventing it. Who funded your travels to Uganda and back?
So we were really fortunate. As a student at Berkeley, I was able to apply for a lot of entrepreneurship competitions. So the first one was the Big Ideas competition at Berkeley. We submitted an application for that, and that was actually a really helpful process to go through of just developing the ideas and like encouraging you to go do those customer interviews and thinking about how you can actually make a sustainable business model from the idea. So yeah, the Big Ideas competition at Berkeley was really helpful, really key. And then yeah, there were some other entrepreneurship competitions, the Institute for International Education Centennial Fellowship, and just other grants that we've been really blessed to be able to help on the project.
Well, great problem solving. Thank you very much, Paige. Congratulations on being a collegiate prize winner. And we're going to now go to another high school invent team, Quarry Lane School from Dublin, California. Quarry Lane, show us what you've done.
Can everyone see the screen? All right. Hey everyone, we're the Quarry Lane Invent team, and just going down from left to right here, we are me, Bridget, and then Harini, Christine, Bryson, Isha, Varshini, Krithik, Karina, and Rachel. Our invention is an effort to help communication between athletes with hearing loss and then sports officials as well as coaches during the game. And we're all super excited to share with you our process and progress with you, so let's do it. Our inspiration for the project came from one particular team discussion where someone brought up a basketball game she played at against the California School for the Deaf in Fremont. Quite often, after the referee's whistle was blown, the opposing players would carry on to finish up a layup or complete a play, unaware that there was an auditory signal to do something else. While hearing loss has no impact on athletic ability, it does impact the flow of the overall game. For example, if a player doesn't notice when the whistle sounds, then the team loses vital seconds in setting up their next play. This also impacts the team's strategy when the coach is trying to tell the team to run a play but can't get the player's attention. So after some discussion, the community problem that we identified was that basketball players with hearing loss have no way of responding to referees' whistles. And then by extension, our team's goal is to reduce these communication delays by improving a player's reaction time to an in-game signal, like a whistle. Through a lot of discussions within the team and interviews with coaches who have worked extensively with athletes who are hard of hearing, we came to the solution of alerting a deaf basketball player through another sense, haptic vibrations. Our device integrates with the referee's whistle, where when the whistle is activated, the device sends a wireless signal that causes a player's wearable device to vibrate. This vibration will communicate specific messages like a dead ball or a coach's further instructions.
Okay, so to understand where we wanted to go with this project, we had to look at the other products that had been made. So firstly, we have the US patent, which is a patent that assists players who are hard of hearing during sport games through a multi-step system involving a whistle, a computer, and a wireless transmitter. It alerts the players with the vibrational west, a loud horn, or visual signals. Secondly, we looked at the Unitec Bracelet, which is an invention that uses a phone as a trigger device and has a bracelet connected to it via Bluetooth. It's intended to encode different haptic patterns to symbolize different messages. And lastly, we saw this Wii Sports, which is a product that works with a trigger device on your finger and a haptic output on the arm pad.
So what makes our device unique from other existing products? Our device is situation specific. The previous products that we mentioned are not specifically designed or intended for use in a basketball game, so they do not account for the game's fast pace or safety hazards. Our device is convenient. Our device is quick to set up, and it's also easy to incorporate with existing gear or implement into a game without a third person's support. Our device is finally adaptable. It is necessary to incorporate existing standards of a basketball game so it can be easily used in any situation. So this is what our device does. So we don't have to design a completely new system because of its adaptability. All right. Now let's talk about our physical prototype.
To evaluate our invention, we checked it against the design criteria that we set for ourselves at the beginning of the project. Our device is safe, comfortable, durable, and unobtrusive. Multiple team members tested it while playing basketball and reported no issues with the device. It is also policy permitted, as the current design of the device is allowed to be worn in-game according to the NFHS rulebook. The goal for our device is to improve the reaction time of a deaf basketball athlete to a referee's whistle. By watching basketball game footage, we determined the current average reaction time to be around 2.5 seconds. Unfortunately, due to the ongoing pandemic, we haven't yet been able to send our ready-to-wear prototype for testing with our partners at Deaf Camp Pacifica and California School for the Deaf in Fremont. Instead, our team did some basic testing ourselves. With our first full prototype, we conducted 10 trials and determined the average reaction time to be 0.62 seconds. So we're pretty confident that our device will be helpful. Now here's a quick breakdown of how our system works. First, the referee is using an electronic whistle, which is a whistle that makes a sound when a button is pressed instead of when it is blown. When the button of our trigger module is pressed, it triggers both the sound from the e-whistle and a wireless radio signal, which is sent to the player-worn device. When the player-worn device receives the signal, it vibrates using a vibration motor so that the player can feel it and be aware of the referee's call. Here are the two main components of our invention: the trigger module and the haptic wearable device. As you can see, the trigger module sends a signal to the wearable device, which vibrates the haptic motor. In the next slides, we will go over the details of each.
For our trigger module, we decided to make it into an add-on component that rests on the outside of an e-whistle instead of actually integrating into the original electronic system, because it is more adaptable and transferable to different e-whistle. The referees are more likely to accept it as the e-whistle hasn't been tampered with. This adaptable concept of our design makes it unique and stand out from other products. As you can see, our trigger module has a push button that sits on top of two other buttons, the button of e-whistle and the button that sends the radio signal. When the push button is pressed, it will simultaneously cause the e-whistle to emit a sound and the radio transceiver to send a signal to the haptic wearable device. Now let's take a look at the components inside the trigger module. It consists of a Fox 40 electronic whistle and a 3D printed casing that contains all the electronics. The current casing is specifically designed for the Fox 40 since it is widely used by the referees. The two main components inside the casing are the NRF radio transceiver and the Arduino Nano. The radio transceiver is used to transmit a signal to the haptic wearable device, which is connected to the Arduino Nano. We tested code that allowed transmission to more than one wearable device. The radio transceiver also has an antenna, which ensures a coherent transmission even when there are many obstacles. Additionally, the Nano board is connecting with a battery and the button that controls the electronic system.
All right, now onto the haptic wearable device, and this module will be worn by the player and it vibrates when it receives a signal from the previously described trigger module. These pictures here just show the electronics, and that includes a rechargeable LiPo battery that charges through a USB-C cable. You can see it working in the top right picture. And there's also a really cool light that turns red or green, depending on whether the charger module is charged or not. And additionally, the slide switch on the left side picture turns the device on and off. The Arduino and radio transceiver are also pictured, and they're like the brains that run the code and receive signals. All the electronics fit snugly inside this 3D printed casing, you can see in the bottom right, and it closes shut with a lid. The one exception is the vibration motor, which has its own separate casing and sticks out, because when we tested it, we actually found that it's a lot easier to feel the vibration when it's separated and on its own. All right, and once those electronics are secured in their little box, the entire thing slides into a fabric band. This band is custom sewn and it has a pouch for the electronics box and a separate pouch for the vibration motor, and this ensures that neither of them slide around during the rough contact of sports. The band is wrapped around the player's ankle, slightly above and on top of the sock so that it doesn't slip, and it stays secure with Velcro. On the right side, you can see some of the materials we used, and the fabric is made of a spandex and cotton blend, which is similar to most athletic attire. There's a layer of Velcro at each end, so that there's lots of room for tightening adjustment. And onto the wireless connection. Here, this video is a demonstration of the device being worn and used while running. And to achieve that wireless connection between the two devices, we're actually using radio transmissions because radios allow us to connect multiple receivers and multiple transmitters, which means we can accommodate for an entire team of deaf players, and we can also accommodate for multiple referees and coaches. At first, we weren't completely satisfied with the range of the device, so we added an antenna to the trigger device that allows the signal to work perfectly at a distance of up to 150 feet, which is more than enough to cover the length of a basketball court. And you can see that in the rightmost picture, that's us testing the range in a parking lot.
We've reached a major checkpoint with a successful prototype, but as a team, we plan to continue this project on our own in the future. Now, in terms of next steps, we plan to test with our outreach partners to get direct feedback about our overall system, so we can make updates and adjustments accordingly. For the trigger module specifically, we aim to produce a more compact version of its casing that fits on other whistles besides the Fox 40 brand, and in addition to some updates on the electronic system. For the haptic wearable device, we plan to adjust the materials used in order to make it more ergonomic. Finally, we want to submit an official patent. We've already filed a provisional patent that gives us 12 more months to develop our product.
We would like to give a special thanks to the California School for the Deaf in Fremont and Deaf Camp Pacifica for working with us on our project as our wonderful partners. We also want to thank the Levelson MIT program and the Quarry Lane School for giving us this amazing invention opportunity and for their support.
Thank you so much, everyone, for listening. Please consider following us on Instagram and checking out our website. You may also reach us through email posted in the chat with any questions, feedback, suggestions, or if you would like to see how you can work with us.
Thank you very much. What a great idea. We've got some questions for you. What if this device gets hacked or gives a false signal? Did you talk about that or consider that?
Okay, that's a great question. I think Kritik can take this one if you wanted to.
Yeah, so the radio transceiver, it's not really connected to the internet as we've said, so I doubt it would really get hacked. However, in case like, if you're wondering about like if the radio transmission like, I guess it could be like intercepted or something. Well, since like there's a direct connection between like the transmitter and the receiver, I doubt that would really happen. And next, for the second part, for false signals, it is one of the reasons why we chose this NRF module, since its transmission strength and consistency was like a lot better compared to the previous ones we were testing near the start of the program. So yeah, it's mainly why we chose the radio. It's much stronger.
Have you thought about other applications that this technology could work really well for? Maybe starting blocks on track events or other types of things?
Yeah, that's a really good question. We have been considering adapting this for different sports. I think Karina can elaborate on that.
Yeah, so that is a recommendation we've been getting a lot, and we actually consider it at the beginning of the project. Not only applying it to different sports, like a starting block for track meets, or even kind of adapting it to a light signal for like, a swimming competition. But we've also looked at some other products that do use it just in everyday life, kind of getting people's attention, just like hanging out. It's kind of like in that case, it's more of like a smaller, more discreet wristband that you wear, and then kind of like your friends can like, if they want to call you over, they can, buzz it or something. So yeah, that's definitely something we want to expand into as part of our next steps and next features.
Amazing. What inspired this idea? How'd you kids choose this product to develop this invention?
This idea originally come from one of our teammates who, when she was playing a deaf basketball game with the players at California School for the Deaf, and we were kind of inspired from there.
So you know the customer, that's really exciting. Does the referee have to point the electronic whistle in the general direction of the players in order for the receiver to recognize the whistle being blown?
So actually, no, if the referee is just in the range, they would be standing generally on the side of the court. So if they were just to press the button, all of the players who are wearing the wearable device would be able to receive the signal.
And just to add to that, that's actually another perk of kind of applying it to a basketball game, is that in general, the court is kind of like the same size. Most of the players are usually in the same direction. So that kind of helps like the situation, makes it a little more consistent that in the case that the antenna were pointed slightly in the wrong direction, the wearable devices should receive the signal.
Great. Can you show your Instagram again? And this is a great job. Congratulations on all the progress you made in spite of the pandemic and everything. It's a very exciting invention. So you can put your Instagram maybe back up on the screen. And we're going to go now to another Collegiate Student Prize winner, Nicole Black. And Nicole has invented something in the Cure It category. Nicole?
Hi, everyone. It's an honor to be here, and especially to see so many people inventing for people with ear and hearing disorders. So it's great to come after that wonderful presentation. So thank you so much for the introduction into the Lemelson MIT program. My name is Nicole, and I am just graduated with my PhD from Harvard in Jennifer Lewis's lab, and have also been working with Mass Eye and Ear Hospital over the past 6 years on this project. And my invention is Phonograft, which is a biomimetic 3D printed and regenerative eardrum graft. To give you some background on the eardrum, it's a thin tissue that separates the environment from your middle ear space and captures sound waves. Unfortunately, your eardrum can become damaged through a variety of mechanisms, including blast injuries, traumatic injuries, and chronic ear infections. And indeed, there are as many as 30 million chronic eardrum perforations that occur worldwide each year. Having chronic eardrum perforations is not ideal, first of all, because it can impact your hearing, as your eardrum cannot adequately capture these sound waves. And secondly, it creates a channel to your middle ear space where water and pathogens can enter and cause additional problems such as meningitis. Your eardrum is actually a very complex tissue, and so in its middlemost layer, known as the lamina propria, it has this highly organized network of collagen fibers in a circular and radial arrangement that aids in sound conduction, essentially allowing your eardrum to behave both like a soft and a stiff material. During normal tympanoplasty, which is the operation for eardrum repair, a surgeon will harvest an autologous tissue, typically fascia, from the patient at the time of surgery and lay it behind the perforation to incorporate. Unfortunately, these graft materials are not ideal. First of all, because they require graft harvesting and manipulation, which many of the surgeons that we interviewed expressed issues with. Additionally, these autologous graft tissues do not degrade or remodel. And so you essentially have a piece of fascia or cartilage or whatever material is used in your eardrum for the rest of your life. And these materials do not have that circular and radial architecture to them. Thus, my invention, Phonograft, is a biomimetic graft that uses 3D printing to recapitulate this circular and radial structure for improved sound conduction. And furthermore, a Phonograft is made from a novel biodegradable elastomeric 3D printing ink. And so what this means is that not only does Phonograft recapitulate the structure of the eardrum, but as native cells grow in and remodel it, it actually becomes tissue matching the structure of the original eardrum. And so we've filed 2 pieces of IP on this invention through Harvard University and Mass Eye and Ear. The first on the device itself and circular radial architecture, and then secondly on this 3D printing ink. And as I mentioned earlier, this ink is unique because as these lines are being printed, they act almost like a software program for the cells to align and deposit extracellular matrix proteins along the structure of the grafts. And so what we're able to see with Phonograft is that it has superior sound transfer over the range of human hearing, which is usually considered to be about 20 hertz up to 20 kilohertz, compared to the standard of care materials, which are fascia and Biodesign, which is a porcine small intestinal submucosa product and is the only non-autologous graft on the market right now for eardrum repair. Additionally, we've been able to perform studies in chinchilla models for chronic eardrum perforations with these grafts. And the reason that we use chinchillas is that they have a similar sized eardrum or tympanic membrane to the human eardrum, and thus we can chronically perforate it and see how these grafts will remodel and regenerate. They also have a similar hearing range to humans. So what this means is we can take a chinchilla with an intact eardrum, chronically perforate it, and then after 4 weeks, these perforations will not heal on their own. They're deemed chronic. And then we can look at these variety of control materials like fascia and Biodesign, as well as the Phonograft, which is a completely synthetic and shelf-stable graft. What we're able to see through these studies are several benefits to Phonograft compared to these controls. The first is lack of invasiveness. So instead of spending time to harvest and manipulate graft tissues, a surgeon could simply open a sterile package containing Phonograft and ideally place it through the ear canal in a clinic setting. Secondly, we've seen higher rates of healing for Phonograft, showing its regenerative nature. And we've seen the ingrowth of native vasculature from the eardrum into the biodegradable material, ultimately meaning that patients may have to undergo fewer revision surgeries. Finally, we've seen improved hearing outcomes with Phonograft. So hearing in our chinchilla models is returned to baseline levels to a statistically significant extent compared to with control materials. And the reason for this really is that biomimetic circular and radial architecture. So as you see on the top right there, this is fascia vibrating at 20 kilohertz, does not have much motion across the surface of the graft. Whereas on the bottom, you see phonograft has these complex modal motion patterns across the surface due to the biomimetic structure. And so overall, phonograft provides a variety of benefits. The first is with surgical feasibility. So it being a synthetic and elastomeric material is easy to manipulate and place. Secondly is with graft adhesion to the surrounding eardrum and integration into the eardrum. The material is biodegradable, which means that as native tissues grow in, the scaffolds will then biodegrade and go away, reducing sites for future infections. The biomimetic structure allows for good acoustic vibration across the range of human hearing. These grafts can also be versatile, so you can think of customizing them to certain regions of the eardrum that may be damaged. And finally, these grafts encourage collagen deposition along the print path and therefore regeneration of the native tissue. And so in summary, I want to think this has been a very collaborative effort between my lab at Harvard under Jennifer Lewis, as well as some collaborators at Mass Eye and Ear Hospital, and some undergraduate students that I've even mentored along the way toward this project who've helped with the material and some of the acoustic testing, as well as some of our funding sources. And so ultimately, we are continuing to push phonograph forward and bring it to the clinic. First of all, to simplify the procedure for surgeons and patients, ultimately to reduce overhead costs due to general anesthesia and increase procedural volume. And finally, and importantly, phonograph aims to improve healing and hearing outcomes for patients that undergo these procedures. Thank you so much, and I'll take any questions.
Thank you so much, Nicole. This is really exciting. What inspired you to choose to get so invested in this work?
Yeah, great question. So my first year of graduate school in Jennifer Lewis's lab, I started working on her bioprinting team that develops, materials for 3D printing of tissue models, really, so bioprinting. But there wasn't really anything super medical device related going on. And so halfway through my first year, I met two surgeons from Mass Eye and Ear, so Doctors Aaron Riemenschneider and Elliot Kozin. And in particular, Dr. Riemenschneider talked about a lot of the patients that he treated from the Boston Marathon bombing. And you may not know this, but actually the #1 type of injury from the Boston Marathon bombing was ear-related injuries. And importantly, eardrum perforations was a large subset of this. And so Dr. Riemenschneider treated a lot of these patients and followed their outcomes over time and was able to see how poor their hearing was, as well as the need for revision surgeries over time following these. And so working in a 3D printing and materials lab, I was really motivated to use these skill sets to design better grafts that would actually mimic the structure of the eardrum and be regenerative for patients.
Wow, awesome. Now, will the body temperature, does the rise in body temperature impact the character of this? Did you run into some issues with that?
Yeah, that's a good question. So our material is stable up to body temperature. It does not melt until a temperature above body temperature. So it's a great question, but we've specifically designed these to be a synthetic polymer and not contain biologics to enhance that stability and ultimately to help with transport. So if you have to get these grafts to regions of the world that might need them, to war fighters that might have damaged eardrums, that these grafts can be stable over time.
Oh, that's excellent, because inside of a container, temperatures can just get caustic almost. Do we understand this correctly? The photograph allows for healing of the perforated eardrum over time. It actually, the natural biological material kind of grows into it and it dissolves out. Is that the way it works?
Yeah, exactly, Don. So it's a synthetic graft that's placed on the eardrum, and then your body actually has a very innate regenerative potential to it, especially in your eardrum. Small perforations, for example, in your eardrum can heal on their own due to the migration of cells from the circumference. So when you place these grafts, they act sort of like a scaffold to guide the cells along the graft and begin to remodel it. And so as these cells begin to lay down their own tissue in this structure of the eardrum, the material itself, the polymer in the graft, degrades and goes away. And so in that aspect, it's regenerative because you're replacing the graft with your body's own tissue in that structure.
Now, when is this going to be on the market? Where are you at in the process of FDA approval or whatever it takes to make this so people can get this?
Yeah, great question. So this is my priority right now after graduation is pushing this forward. And so we're going to be going down a 510K clearance process through the FDA because there is one product in the market already, that Biodesigned by Cook Medical, that we can claim substantial equivalence to with the appropriate studies. And so it's a relatively short process compared to other medical devices, but still requires some design finalization. So hopefully within a year and a half to 2 years, this will be on the market for patients.
Wow. We do have a question. What did it cost you? You said you had a couple of patents or provisionals. What did it cost to get a patent?
Yeah, good question. So these are all filed by Harvard University and Mass Eye and Ear. So the patent, costs really range based on what stage you're at. So, provisional patents can be like $10,000 up until a full patent that you file in multiple countries, as we did with our device architecture patent, can be around $100,000. So usually in that range. Yeah. So we're very lucky to have been working with Harvard Office of Technology Development to file that IP.
Yeah, we have one more question, and that is applications of this technology outside the eardrum. And have you thought about licensing the technology, especially if it could be used in other medical areas?
Yeah, definitely. So other markets are definitely of interest to us. And in particular, when I was writing up these patents and our claims, we made sure to include a lot of additional tissue graft markets. For example, any tissue where the structure is important to its function. So you think cartilage, in particular, there's a type of cartilage called articular cartilage that has an orientation to it that's important. Also thinking about vascular grafts, muscle grafts, and nerve grafts, where the alignment of cells in these tissues are important. And so, yes, our team has just finished licensing the technology from Harvard.
Wow. Well, thank you, Nicole. Great job. Congratulations to you and your team on being recognized as a collegiate prize winner also.
Thank you so much to the Lemelson. Yeah.
Yes. And our next team, our final presentation, is a high school invent team. It's Charles R. Drew Charter Senior Academy from Atlanta, Georgia. And they have a really interesting little device that they've created. Charter Drew?
Hello, my name is Owen Grega. I am the administrative lead and a member of the hardware team. We are an engineering team that attends Charles R. Drew Charter School in Atlanta, Georgia. We all came together because of our love of engineering and for the wealth of experience you would gain from this project. Although this project has been a challenge and there have been many ups and downs, we've pushed through and created something we can all be proud of.
Our device focuses on combating police brutality and putting an end to unjustified stops. According to the Prison Police Initiative, when police initiated an interaction, they were twice as likely to threaten or use force against Black and Hispanic residents than white residents. For those that used their body cameras for the entirety of their shift, there was a noticeable decrease in forceful interactions. Meanwhile, those that were able to turn their cameras off, there was no change in behavior.
Hi, my name is Zachary Harris, and I am a data team lead. Today, I will be reading the invention statement. Police officers in the United States disproportionately pull over, cite, arrest, and even use lethal force against people of color. Even with the implementation of police body cameras, their effectiveness has proven to be minimal. Our device centers around the most prevalent cause of interactions between police and civilians, the traffic stop. It is a dash-mounted integrated system that has three main goals: reduce unnecessary targeted stops, improve interactions between police and civilians during traffic stops, and provide protected video, motion, and location data about traffic stops that is available to the civilian immediately via a web app. The device will upload audio and video to a secure server and will allow the driver to interact with the vehicle data. We will not make this public.
Now we are going to hold a moment of silence for all of the individuals who have been negatively impacted by the effects of police brutality in America. Although we are unable to call out every name, we wanted to acknowledge these people. Now we can move on to the next slide.
Hello, my name is Caitlin Smith, and I'm on the machine learning team. While our main intent for our device is to combat racial injustice during police stops, all drivers can benefit from our device. While our device captures police interactions, it also captures the driver's behavior. Our device will not only protect the driver, but will support all parties of the interaction to make safe and just decisions.
Though there are various body cams and vehicle cameras on the market, our device specifically targets police interaction from the civilian's point of view. In addition, our device functionally offers data pre-interaction, discouraging the driver from any erratic motion or illegal activity in the first place, and in the event that it is needed, offering any necessary data and information about the car's motion and driver's activity.
Bye, Miss White. All right, you too. Yeah, I'm getting in the car right now. All right, y'all see you soon. Love you too. Bye.
Oh no, Quinn is being pulled over. Now the average civilian might be a little alarmed, but no need to worry. Quinn has stopwatch.
Okay. Yeah, I know I have my seatbelt on. My phone is in my bag. I wasn't speeding, so on the speed limit. I'm doing good. How about you?
Yeah, you rolled past me back there. I noticed you weren't wearing your seatbelt.
No, I had it on. I actually just took it off when you had pulled me over, just made sure everything was stopped, turned off, and everything.
You sure about that?
Yeah, I'm pretty sure.
Okay. You have your ID and insurance on you?
Yes, my bad. Hold on. All right, here you go.
I'll be right back.
Okay.
All right, so here's a citation for no seatbelt. You can fight it in court. Your court date is going to be in about 2 weeks. The date is here at the bottom. Your ID and your information back.
All right.
All right, make sure you follow all the traffic laws.
I know I have my seatbelt on. So I'm going to check my app when I get home. All right, now that I'm home, I need to check that video to make sure I have my seatbelt on, because I know I had it on. All right. Yep, I know I have my seatbelt on. I'm going to take this to court with me when I go. Bye, Miss White. Bye, Quinn. Have a good day.
Now that you know a bit more about our device, we're going to share the individual components that make our invention functional. My name is Lillian Martin, and I am a member of the hardware team, and I worked on the GPS this past year. The GPS collects location data via the satellite. This data is recorded as latitude and longitude points, which is converted into a file and uploaded to Amazon Web Services.
I'm Alexandria Sweeney, and I was the hardware team lead. My goal was to get the microphone to record audio and then upload it to AWS. Currently, my code works with the machine learning code, so when the device is run, the camera detects objects at the same time that audio is being recorded. Once the audio is successfully recorded, it is automatically uploaded to AWS.
The camera of our device will have two functions. One, to record any traffic stops, and two, to allow machine learning to detect a seatbelt or phone in the driver's hands while driving. I was in charge of completing the recording function of the camera. The camera works by pushing a button on the device. It will start recording, and it will continue until the button is pushed again, stopping the recording. After being recorded, the video will be uploaded to our online database, Amazon Web Services. From there, it will be made available on our web app.
My name is Chanel Harris. I was the research lead and a member of the hardware team. I worked with the accelerometer,
The goal of the accelerometer was to determine if a driver was driving erratically and upload the saved data to AWS. The module begins collecting data once initiated by the button with a green light indicator, saving the data to a file once every minute. The collected data is then uploaded to AWS as a CSV file. We have not yet been able to determine a threshold to indicate erratic motion.
My name is Drew Williams, and I am the machine learning team lead. Our goal was to implement machine learning technology with the intentions of getting our camera to recognize a seatbelt and the usage of a cell phone.
As shown on the slide, there is an object recognition list that is made via machine learning. We use this information to determine whether the user is wearing a seatbelt or not. It is also capable of detecting if the user is using a phone. Finally, we compile this data and store in AWS.
On the left, there are two visual indicators shown, a bumper sticker with our device logo and a visual indicator that is mounted on our car roof. The image in the middle is showing what our device will look like mounted on the dashboard, and the image on the far right shows what the recorded view from our device will look like during a traffic stop.
The data team was able to make a database where information from our invention automatically uploads, organizes, and stores our data.
My name is Quinn Washington. I'm also a lead on the data team, and using AWS or Amazon Web Services, we created a database where we can automatically move, store, organize, and move our data straight to our web app from the device.
Good afternoon. My name is Maya Crowell, and I'm the UI team lead and sustainability lead. So in this video here, you're seeing an example of our web application. Our goal was to design a functional user interface, or the manner in which a user could access our device online. And so they are able to query video, audio, speed, and motion data on this site. And once you log in, you're able to see these tabs at the top. For example, with the video data, you're able to click Show, and this will show you the video that you've uploaded. And once you play this video, you're able to full screen it and move to different parts. And then once you go back to the main page, this is just your gallery, and you're able to edit the video's title. And the same goes for this other section called Motion. And this is where you could update your spreadsheet of motion data that you got. For example, the speed data that Quinn got when he was in the car. And you're also able to upload it from the actual computer's hard drive. And so this page here is just a screenshot of what was shown in the video. And this is just a close-up of the video page and the motion data page.
In the first screenshot, it shows the profile page where the user can create their profile, edit their credentials, and cancel their account. The second two screenshots shows the map page where the user is able to receive their location data, and the points are then displayed on a satellite map. Lastly, the user is also able to sign out via the navigation bar.
Our next steps are to finalize the remaining hardware functionality, primarily the GPS, test our data and identify thresholds for erratic motion, continue to iterate the web application to finely tune an effective user interface, and test the product with users.
We would like to thank the Limos and MIT program, Wells Montague, our tech mentor, the Drew admin team, members of our community who have provided input, Michael Crowell for behind-the-scenes development help, Claire and Jatine Vodka for Ruby on Rails troubleshooting and mentorship, Miss Crowell, Miss Williams, and Miss Washington for InvenTeam gifts, our Drew family, donors who have provided funding or materials/supplies, and Miss Terry Gay. Thank you.
Thank you. That was a great presentation. Very interesting. Can you elaborate on how you trained your machine learning model to recognize seat belts?
Yes, that'd be a great question for a member of our machine learning team if Jason Lind would like to answer that question.
Sure, I can take that question. So the way that we trained our machine learning module was by inputting a large database of users wearing seatbelts, and that eventually improves the model at recognizing seatbelts.
Wow, cool. How did you gather feedback during the invention process?
We did have a survey, and if Chanel Harris would like to take this one, she was a big part in that.
So as the research lead, I conducted a survey and sent it out through the community, consisting of civilians and law enforcement to get their opinion on our device and thoughts. And I will say that through their feedback, we have made a major change in our invention, that the video file and information about the stop will no longer be accessed publicly. It will be first sent to a private server via the web app.
So I was curious that storing video is not cheap. What does AWS cost you? What's it cost to store the video, and how long is it available for?
If we'd like to hand this question over to Quinn Washington on the data team.
Okay, so AWS is just like under all of like Amazon's other stuff you can pay for it. It's a subscription, and we have unlimited use for a specific amount of data. I think it's a couple terabytes of data that we're allowed to store. So we can make as many buckets as we want to organize the different types of data that we have. So we have to keep paying that subscription so that we can keep your data safe in there.
Now, you made this web app. How are you kids part of a computer science program? How'd you learn how to make a web app?
If Maya Crowell would like to take this one.
And it was a bit of a learning curve, learning how to actually code with Ruby on Rails. But when we first began our invention, we met with a mentor who recommended the program because it was a relatively easy learning curve if you already knew like some basics about code. And so we took YouTube courses, and we reached out to some people in California that we mentioned in our acknowledgements, Claire and Jatine Bhakta, who helped us along the way.
Now, how does the upload link work? Exactly. I'm sure there has to be some kind of security so that this could be admitted in court if it was used that way.
I'm assuming you're talking about the upload where it says like upload file from the computer. And
Yes.
so that's where the login comes in and where it's user specific. So like in any site that you would use, like say YouTube, for example, where you can go in, log into your account, and then select what you would want to be uploaded, it works the same way.
Okay. What hardware, like what's the resolution on the camera? How'd you pick your hardware? Can you tell us a little bit more about the hardware itself?
Yeah, I could speak to at least the camera a little bit. The camera we were using was made for the actual motherboard we were using. We were using a Raspberry Pi motherboard. And so on their website, they have a bunch of different accessories you can use, which we were using. And the camera, it was just a generic, I believe it was a 720p camera, which is definitely something that we'd want upgraded in a final iteration. This was all just for the development process. But I mean, we definitely want a higher resolution camera in the final device so that we can actually, you want to be able to see what's going on. You don't want anything, unknown. You'd like to be able to know it or be able to see everything.
Now, have you considered having a camera both inside and outside the car? Because sometimes an officer will ask you to step outside the car, and I assume that would become off camera, but you'd still have audio. Can you kind of share with us what your thoughts were on that?
Yes, so having another camera was definitely a thought. I don't think we talked about it for very long, mainly because it was just a hardware limitation. Like I said, the Raspberry Pi we were using, especially the one we were using, it was a lot smaller and had limited capabilities, but there's only place for one camera to be on the device. So this is just, constraints we had with the actual devices we were using. But I mean, it was definitely something we talked about. We also talked about trying to use data from the actual car itself, like the backup camera. but all the data inside a car like that is just so well encrypted. It'd be so hard to actually get into a car's, firmware and get that data for our device. So it was just a bunch of, constraints and things that we couldn't pass.
So this is awesome how all of you have worked together on this. How did you divide up this work? Can you tell us a little bit about your team structure to get this to all come together?
Yeah, so it actually started during the application process. There were multiple parts of the application, so we all kind of broke off into different teams, and those teams kind of, slowly developed into our teams we have now. We have 4 main teams. We have a hardware team, we have a data team, a machine learning team, and a user interface team. And so they just, it was something we knew from the beginning. We knew that we were going to have, this device has a lot of different parts that need to be done. The actual device itself, making sure the camera, the GPS, the accelerometer are all working properly. And then that data needs somewhere to go. So that's why we have a data management team. The data management team is, in charge of storing that data and organizing it. So then we can move it from the data management to the user interface, or the user can actually access the data they received from their car. And then the machine learning was, it was a completely different story. It was very complicated. It's, working with AI and trying to get the device to, learn how to recognize different things like a seatbelt and a phone in the user's hands. So that would also need to be a team on its own. But we had so many parts of the project, we had to break it down. If we were all trying to work on the same things, it wouldn't have been, reasonable. We'd be wasting time. There'd be too many people working on one thing. So, we needed to break it up so we'd have multiple people working on different tasks, and we'd all came together towards the end to try to work on integration between all of them.
Excellent. Now, was this a class that you kids were in, or was this an after-school program, or how'd you all come together as a team?
So a lot of us have been in the same class since freshman year, and even before that in middle school. But the way this class worked is it was an option. So we were told about this the year before when the application process started, and we did that first round of applications. And we kind of got to decide if we wanted to be a part of it. We knew it'd be different from our normal, engineering pathway class. So it was a class that was took place during school, but it was different from the normal class. The actual class itself was called Engineering Applications as part of the pathway. So there were other engineering application classes that had normal, our school curriculum. And then we had the Engineering InvenTeam class that did our own thing with the InvenTeam project. So yes, it was a class, and we did it during school.
How much of
outside of school?
How much of the time was virtual, and how much of it was in person?
99.9% of it was all virtual. There was one class period we were able, the hardware team, so there were 5 of us, including our teacher, that we were able to meet towards the end of the school year, because for most of the project, all of the people on the hardware team were working on their separate devices and making sure they were functional. So I was working on the camera a lot of the time, and I was just working on the camera. I had to focus on that and make it as good as I could. So towards the end, we all had to come together and work on getting them all to work together off of the same device. So most of it was virtual, except for that one class period we had together.
Now, are you kids familiar with Ring doorbell? Do you feel that there's any similarities in the technology between Ring doorbell and what you're doing?
You could say there's a lot of similarities to just normal dash cams that are in cars right now, but we wanted to focus our device on specifically police traffic stops and trying to work towards fighting the racial injustice that we've been seeing, over the past couple of years. And we wanted to do something that specifically targeted that and helped fight it. So yeah, there's a lot of similarities, but we wanted to also make it different. So we have the camera, we also have the accelerometer checking erratic motion and GPS checking speed data, and the part of it that's also uploading it all into a database, and so the user can use it. Hopefully they don't have to, but being able to access it and use it for court dates and things such as that. Yeah.
Well, I know a ton of parents who would absolutely love to have access to this with their teenage drivers. Did you talk to parents at all, or have you discussed the opportunity for kids to gain greater trust by allowing parents access to this kind of technology?
Yeah, and that was actually, some of that was talked about in the survey. If Chanel Harris would like to talk about this a little more.
I will say one main concern that I believe parents had was the idea of a big brother, I guess, like sort of watching over them with the data collection always being present. So that's something we had to take into account. But I don't believe we have discussed really the application of it towards teenagers with it being related to their parents and their wants.
Well, interesting. I think you have a huge opportunity there. The statistics for insurance on teenage drivers, even it would seem to me like this kind of a device would help you with your insurance costs potentially if it was commercially available. So thank you very much. Great job, Drew Charter School. And thank you for your presentation today. So everyone, thank you for joining us here for EurekaFest as we celebrate these collegiate prize winners and these high school inventors from the InvenTeam program sponsored by Lemelson MIT. And I would encourage you to go to the website. All of these presentations are recorded. We are one group. There was 3 other groups. There's I forget if there's 15 or 16 InvenTeams and several collegiate student prize winners, and all of these folks have just done a tremendous job. And I know from experience as an InvenTeam teacher, the growth that occurs for both the students and the teachers is just absolutely incredible. This is the premium invention experience for high school students in the United States today, in my professional opinion. So we thank you for joining us. If you have, you can of course post in chat if you have any additional questions or comments. And thank you to the teams. After this, I believe at 2:30, 11:30 Pacific time where I'm at, we're going to start a design challenge with the InvenTeams. And we'll be looking forward to seeing what you folks invent using the microbit and some other components. Thank you very much to SparkFun for helping us with getting those pieces of equipment out. And we look forward to what the InvenTeams will create during the design challenge time. Of course, there's EurekaFest is continuing into tomorrow. Take a look at the EurekaFest website and be sure and sign up for additional presentations. The presentation from Dr. Seema and the other gentleman from MIT this morning on energy. Energy is a major concern for all of us. That was a very insightful presentation, and we look forward to all of you joining us for additional EurekaFest events. Thank you again.